3.7 rates of change. This section is just asking us to go through some examples and see where rates of change are applicable in the real world. So the first and most common place you'll see them in a math class is its application to physics problems. So here we have a standard problem. I think this is actually the problem we looked at on day one where we were only able to estimate the velocity of the rock, but now, since we have derivatives and a lot of shortcuts, this is much easier. So a rock is thrown straight up with an initial velocity of 45 feet per second. The position of the rock is given by the function s of x equals negative 16x squared plus 45x. Now keep in mind that is the position, not the velocity. So the velocity is how fast is that position changing over time. The way we figure that out, of course, is with a derivative. So we need to know what is s prime of x first of all. And by this point, we're all very familiar with taking the derivative of a polynomial function. We get this. But what we really want is what is that speed, that velocity at 1 second. So I really want to figure out what is s prime of 1. So I just plug 1 into x, and that tells me that the velocity is 13 feet per second. All right, nice job, you rock. So now we want to find the acceleration after it's thrown. We haven't actually done this in our class yet, but the idea is that acceleration is how fast our velocity is changing. So if we look at our derivative, s of x, really, s prime of x, we can think about how fast is that changing over time. And to do that, well, we just take another derivative. So acceleration is s double prime of x, second derivative. Well, since we already know that the first derivative is negative 32x plus 45, that means acceleration is negative 32. And of course, the units on this are feet per second squared. What we're really interested in, of course, is the acceleration of the rock at 1 second. Well, we don't have an x to plug 1 into, so of course that just is a constant, negative 32 feet per second squared. So in other words, no matter where the rock is in its trajectory, our rock has a constant acceleration of negative 32 feet per second squared, which should correspond to your understanding of gravity at this point. All right, let's move on to a different application. We see applications of derivatives in biology. So here's a basic one. A population of bacteria starts out with 3,000 units and doubles every hour. How fast is the population changing at 10 hours? So at the first hour, at 0 hour, it's 3,000 units. Since it doubles every hour, then after 1 hour, we'll have 6,000 units, and then 12,000 at the next hour, etc. So how fast is the population changing at 10 hours? Note, it's not asking you to figure out how many units the bacteria have at 10 hours. It wants to know how fast it's changing. So the way we do that is how fast it's changing should always ring a bell with you from now on, that we want to find the derivative. So first of all, we need to figure out what is the function. Well, I'm going to use t as my variable. F of t, if it's doubling every hour, that means every time we have a new hour, we need to multiply by 2. But since we're talking about doubling every hour, that means this is an exponential function with 2 as the base. So after the first hour, I'll be multiplying by 2 to the 1. That corresponds to the 6,000 units. After 2 hours, I'll be multiplying by 2 and then 2, so 2 squared. And that will correspond to 12,000 units. So the only problem with my function at this point is I don't have anywhere that it starts at 3,000. Well, the way we handle that is if we just start it at 3000 and then multiply by 2 to the t, now this should work, because if you plug in 0 for where we're starting at 3000, you get 3000 times 2 to the t. If you plug in 1 then into t, then you have 3000 times 2. That means it's doubled after the first hour. If you say 3 hours, plug 3 into t, now you're talking about 8. And so the 3000 has been multiplied by 2 times 2 times 2 for all 3 of those hours. So this is our function, but because it's asking how fast is the population changing, we need to find the derivative of this. Alright, so I'm just looking at the 3000 and calling that a constant multiple, so it's going to come along for the ride. Now, if we take the derivative of 2 to the t, that is 2 to the t, but since it's an exponential function, that is multiplied times the natural log of 2. Alright, then it wants to know how fast is it changing at 10 hours, so we just simply plug in 10. 3000 times 2 to the 10 times ln of 2. So if you want a decimal approximation, throw that into your calculator. Alright, now you might be asked, essentially for the acceleration piece, how fast is that growth increasing at t equals 10 hours? Well, we know that the derivative was 3000 times 2 to the t times ln of 2. So f double prime of t is going to be to the derivative of f prime of t. To figure this one out, just think of ln of 2 and 3000 as our constant multiples. 3000 2 to the t times ln of 2. But because we took the derivative of 2 to the t, now I'm multiplying times another ln 2. So this f double prime is really 3000 times 2 to the t times ln of 2 squared. And don't try to use any log rules on this. The exponential log rule only applies when the exponent is on the inside argument. But here we're squaring the entire natural log of 2.